In the last lecture, we have seen how to use the Milne-Thompson method to find the analytic function and the harmonic conjugate of the given function. Now we have to move onwards. So we'll see how to find the orthogonal trajectory. Okay, so as we know, for the orthogonal trajectory, we have seen if I have the function to be analytic, then I am able to find the orthogonal trajectories, and precisely the real part and imaginary part are the orthogonal trajectories of each other. So if we consider the family of curves, u is equal to c1 and v is equal to c2, then we can say this family of curves u is equal to c1 form the orthogonal trajectory for the family of curves v is equal to c2. Okay, and now we have to find if one is given. Okay, so let us try some examples based on this. So we try the example based on this. So we say find the orthogonal trajectories of the family of curves so we have the family of curves x cube y minus xy cube is equal to c. So here this is given a family. So we can consider this either as u or as v, and we have to find the other. Okay, so as we have to go through the analytic function, so we first consider the analytic function. So let we have f of z is equal to u plus iv be the analytic function. Okay, and then with now it depends on us whether we consider this as u or v. So with I'll consider this as a real part u is equal to. So we got x cube y minus xy cube is equal to c. Okay, so where c is going to be constant. Now, as we have to use the Milne-Thompson method, so we consider the first step we have completed. Consider the second step. So we have consider we are considering a real part. So phi 1 is equal to dabba u by dabba x. So this is going to be 3x square y minus y cube. Let this equation 1. And we have phi 2 of xy is equal to dabba u by dabba y. So this is going to be x cube minus 3x y square. So let this equation 2. Now the third step we have to consider, and hence in third step what we do is we put x is equal to z and y is equal to 0. So we can have put x is equal to z and y is equal to 0, we get. So what we are having here, see the term. So it is going to be phi 1 of z0 is equal to. So here this y is 0, this y is 0. So the function is going to be 0. And phi 2 z0 is equal to. So what we have here, this x is going to be 0. So I'll be having z cube minus this term is going to be 0. So y is going to be 0. And hence we can have this z cube only. So now we got this phi 1 of z0, phi 2 of z0. So the fourth step we can apply by Milne-Thompson method. So what we have, the analytic function f of z is given as. So what is the formula for f of z by Milne-Thompson method when the real part is given? So it is integration phi 1 of z0 dz minus I integration phi 2 of z0 dz and plus, now c is already given to us. So we have to use c1. So where we declare that c1 is constant of integration. So it is going to be the constant of integration. Now we have to put this value. So phi 1 we have, phi 2 we have, and hence we are able to get phi 1 and phi 2 as. So what we get here, we have f of z is equal to integration 0 dz minus I integration z cube dz and plus c1. Okay, so that's what we have. Now simplify this. So we can have this as, this is going to be minus I z raised to 4 by 4 and plus c1. So we got f of z is equal to minus I by 4 and you will be having z raised to 4 plus c1. So is the analytic function. Okay, this is the analytic function, but what we are interested in finding the orthogonal trajectories. And hence, what we have to do is, if this is the analytic function, then we have to separate the real and imaginary part of this analytic function. So what we do, the next, put z is equal to x plus iy in above equation. We get, so what we'll get here, if I write f of z is equal to minus I by 4 and this I'll be having, so x plus iy bracket raised to 4, okay, and plus c1. So what we know is, we know a plus b bracket raised to 4 is equal to a raised to 4 plus 4 a cube b plus 4 6. Okay. So we are using binomial theorem. So 6 a square b square plus 4 ab cube and plus b raised to 4. Okay, so this is what we have. Okay, and now using this, we are able to expand this. Again, what we know is, we know I square is equal to minus 1, I cube is equal to minus I, and I raised to 4 is equal to 1. So if we expand this using the binomial theorem, then it is minus I by 4. So let us expand this, solve having x raised to 4, then plus 4I x cube y, okay, minus 6 x square y square, and here we'll be having minus 4I x y cube and plus y raised to 4 plus c1. So see here, a is going to be x and b is going to be iy, and then we know I square. So here we'll be having y square, I square, y square. So I square is -1. That's why I have taken it here. Here I'll be having I cube, y cube, and hence I cube is equal to minus I. So I have written minus I. Then here I raised to 4, y raised to 4. So we have I raised to 4 is equal to 1, and hence we have here this is going to be y raised to 4. And now what we have to do is we have to multiply by this minus I by 4 inside. Okay, so what is the term I'll be having? Minus I x raised to 4 by 4. Then this term, so 4 will get cancelled, and I square is equal to -1. Already we have minus, so I'll be having plus x cube y minus minus plus 6I by 4 x square y square. This will be minus minus plus, but I square you have, so it will be minus x y cube minus I y raised to 4 by 4 and plus 7. Now what we have to do is we have to collect the terms without I and the terms with I. So we'll have x cube y minus x y cube and plus I. I'll take I by 4. So I'll be having 6 x square y square minus x raised to 4 and minus y raised to 4 and plus 7. So this is the term we have, then this is the term we have, and this is the term we have. So we got all the terms, and hence this is going to be f of z. Okay, and now we can compare the real and imaginary part. So we can have comparing real and imaginary part. We have, what we'll get is u is equal to x cube y minus xy cube, and v is equal to 1 by 4 6 x square y square minus x raised to 4 minus y raised to 4. So we know this is a, if I equate this to be a constant, then it will be a family of curve. So if I equate this to a constant, it will be a family of curve. And we know this family is orthogonal to this family. So this is actually the orthogonal trajectory of this family. And hence we can say the orthogonal trajectories of the given family of curves is, so what will be having 6 x square y square minus x raised to 4 minus y raised to 4 is equal to constant. So see, if we write 1 by 4, this time is equal to constant, then I can write this is equal to 4 times C2, which is again a constant. So that's why I have written directly this term is equal to constant, because this constant we can have on the other hand side. Okay, and so we can write directly this equal to a constant. So this way we are able to find the orthogonal trajectories of the given family of curve where C2 is a constant. Okay, so when you write equal to constant, that means it is a family of curves. When you do not write equal to constant, then this is only the one curve. Okay, so that's what we have. This is only going to be a curve, but this is the family of curves. Okay, so do you have any doubt in this example? So do you have any doubt in this example? Okay, that's good. Okay, so let us have the another example. Okay, so we'll consider the another example. So we can have find the orthogonal trajectories of the family of curves. So we have this family of curves ex square y plus 2x square minus y cube plus 2y square. So we can say this is minus 2y square is equal to constant. Okay, so that's what we have. Now this is the family of curves given as this C gives the family, C generates the family. So that's why this is the family of curves given, and we have to find the orthogonal trajectories to this family of curves. So let us consider. So let f of z is equal to u plus iv be an analytic function with a real part u is equal to 3x square y plus 2x square minus y cube minus 2y square is equal to c. So here it is not given that whether it is going to be u or whether it is going to be v. So we have the choice. You can consider u also, you can consider v also. So that doesn't matter. Okay. So if we consider this as u, we have to find v. If we consider this as v, we have to find u. Okay. So now we have to go through the Milne-Thompson method, and hence we consider the next step. So consider phi1 of xy is equal to w by wx. So we have this is 6xy plus we have 4x, and let this equation 1. Okay, and we have phi2 of xy is equal to w by wy. So here we have 3x square. Then with respect to y, we have to consider. So 3y square minus 4y. So this is equation 2. Okay. So we got this with respect to x, with respect to y. And now we have to consider the third step. So what we do in third step, we put x is equal to z and y is equal to 0 in equations 1 and 2. So we have, so what we'll get after putting this values here. So we can have that phi1 of z0 is equal to 4z, and we have phi2 of z0 is equal to 3z square. This term contains y, so that's why this term is going to be 0. These both the terms are having y, so we are putting y is equal to 0, and hence these two terms vanish. And now we have the fourth step for Milne-Thompson method. So by Milne-Thompson method, okay, the analytic function f of z is given as, so what we have, f of z is equal to integral phi1 of z0 dz minus I integral of phi2 of z0 dz plus c1. So please be careful. We have already used c, so that's why we cannot use it once again. And hence we write this as c1. So where c1 is constant of integration. Okay, c1 is going to be constant of integration. And now put up these values of phi1 and phi2. So we have f of z is equal to integration 4z dz minus I integration 3z square dz plus c1. Okay, so we can have this integration as 4z square by 2 minus I 3z cube by 3 and plus C1. So we can write this as f of z is equal to 2z square minus iz cube plus C1 is the analytic function. Okay, so now we got the analytic function, and hence we have to separate the real and imaginary part of this analytic function. So what we can do is, next step, put z is equal to x plus iy in above equation. We get. So what you are able to get is f of z is equal to. So you will be having 2x plus iy bracket square minus I times x plus iy bracket square bracket cube here and plus C1. So what we know is, we know a plus b bracket square is equal to a square plus 2ab plus b square, and a plus b bracket cube is equal to a cube plus 3a square b plus 3ab square plus b cube, and we know I square is equal to minus 1, I cube is equal to minus I. So using this binomial theorem for the expansion of square and cube, we are able to find this is twice x square plus 2ixy minus y square minus I, and you will be having here x cube plus 3ix square y minus 3x y square and minus I y cube plus C1. Okay, now simplify this. So we have, this is 2x square minus y square plus 4ixy. Now we have to multiply by this minus I inside. So if I multiply by minus I have minus ix cube. Then this I and I will become I square, and this minus will become plus. So we'll be having plus 3x square y. This minus minus will become plus, and we'll be having 3ix y square. So you'll be having this minus and minus plus, and you'll be having 3ix y square. Then this minus and this minus will become plus, but we have I square. So again you'll be having minus y cube and plus C1. And now consider the terms without I and with I. So we'll be having here, this is 3x square y minus plus we can have 2x square minus we'll be having y cube minus 2y square. 2y square. So this is the term without I. Then plus I 4xy minus x cube plus 3xy square. Okay, so this is the term you'll be having with I and plus C1. Okay, so this is what we have got f of z. So we got f of z, and now what we can do is, we can comparing real and imaginary parts we have. So what we can have is, we get u is equal to 3x square y plus 2x square minus y cube minus 2y square, and we get b is equal to 4xy minus x cube plus 3xy square. Okay, so we need to check whether we got it correct or not, or whether our calculation is correct or not. So check the given function. So what is the given function? 3x square y plus 2x square minus y cube minus 2y square, and see what is the real part that we have obtained. So it is exactly same what we was given to us, and then what was given to us is exactly same as this. So we have calculated everything correctly, and hence now we can write the orthogonal trajectories. So the orthogonal trajectories of given family of curves is, so what we have here, this is 4xy minus x cube plus 3xy square is equal to C2. Okay, so we can write here where C2 is, okay. So this way we are able to get the orthogonal trajectories for the given family of curves. So this was the given family and we used it and then we calculated the analytic function using Milne-Thompson method, and then we calculated or we separated the real and imaginary part, and after that we have equated the remaining part or the p with the constant to form the family of curves. And once we know the family of curves, then we know that this family is the orthogonal trajectories of given family of curves. So, do you have any doubt in this example? Yeah, yes, that's a good question, Gaurav. Okay, what is the significance of finding the orthogonal trajectories? Very nice question, actually. Okay, so the okay, ask him to join again. So the application of this is actually in many fields. Okay, as I told you, one is the magnetism, electromagnetism. Then we have thermodynamics, and then heat and all. Okay, so one thing I'll tell you. Okay, how many of you have opened the CPU of your computers? Okay, most of the times we have laptops nowadays. Okay, but if any one of you have a CPU at home, the desktop, how many of you have opened CPU? Is there anyone who has opened CPU? Yeah, okay, someone is there. Okay, haven't opened but seen the internals. Correct. Okay, no problem. Okay, now the question is when we buy our computers, okay, we always think of the most three important things. What is the RAM? What is the processor? And then what is the hard disk? Okay, so these three things we precisely see. Okay, then we see what is the remaining configuration like screen resolution and remaining things. Okay, but when we think of RAM, processor, and the storage, okay, then now I am coming to the important part. How many of you seen the motherboard? Yeah, we know, but most of the time, yes, motherboard you have seen. Correct. That's good. How many of you have seen the processor? Processor, have you seen the processor? Okay, yes. Okay, now, yeah, you have assembled. That means you will clearly able to understand what I am going to say. Okay, so we have a motherboard, and then on the motherboard, we assemble everything. Okay, so we assemble RAM on motherboard. We assemble LAN card on motherboard. Sometimes LAN card is inbuilt. Okay, but we assemble the different adapters on the motherboard. Okay, the most important thing is that when we assemble or when we put the processor on the motherboard. Okay, so usually when we use the computer, due to this processing on the computer, actually it is processed on the processor, and hence it generates heat in the processor. Okay, so when we think of the heat generated in the processor, then the amount of heat generated in the processor is directly proportional to the usage. Okay, or is directly proportional to the number of processes being processed on processor. Okay, and hence the important thing is that what will happen if we do not take care of this heat. Okay, so suppose we do not take care of this heat, heat is being generated, so the temperature of your processor will go on increasing, and one time it will come that it will burn out. Okay, so it is very bad if your processor goes off, then your computer will not work, and this is due to the, yes, this is due to the heat that we have not yet taken care. Okay, so the problem is, am I able to replace this processor very easily? Okay, so if you go and buy the processor, it will cost at least you 2,000 to 4,000 rupees. Okay, and again, if you put the same processor, it will burn out in 2.5 hours. Okay, so is it feasible to use any machine who is asking you for 2.5 thousand to 4,000 for 2 hours or 3 hours? Will you use such machine? No, definitely not. We are not going to use this machine. Okay, so this is happening due to only one cause, and that is the heat generated in the processor. Okay, and now you see there is a metal case, okay, attached to the processor. Okay, so there is a metal case attached to the processor. It is called as heat sink. Okay, it is called as heat sink. And now one geometry you need to understand. Okay, so what is the geometry? This heat sink is exactly perpendicular to the processor. Okay, this heat sink is exactly perpendicular to the processor. So here comes the orthogonal trajectory. Okay, so here comes the orthogonal trajectory. So the curves that are made on this heat sink is a family of curves which diagonally or which intersect the heat curves, which are called as isotherms. Okay, so the source of heat is the processor. The curves of the family of heat, which are called as isotherms. Okay, so this isotherms is one family of the curves, and heat sink is the another family of the curves, and these isotherms are exactly perpendicular to the heat sink, or actually we know the isotherms and we design the heat sink. Okay, and that's why this isotherm is the given family which we know actually. Okay, so this is the given family of curves, and accordingly we design the heat sink, so which is the orthogonal trajectory. Okay, and that's why when they are exactly perpendicular to each other, then only the heat is absorbed in maximum proportion, and the temperature of the processor is controlled. Okay, and if the temperature of the processor is controlled, then only we are able to use it for the long time. Yeah, and that's why this is the mathematics behind that heat sink, the metal case, and the source of the heat generating. So, which is actually the processor. Okay. Nowadays, we don't require the AC rooms for our computers, but in the back eras of 90s, okay, so then it was a mandatory condition for a computer lab to be air conditioned. okay, to control this temperature. Okay, nowadays we can use our machines anywhere because we have put extra fans to cool it. Okay, and not only we just do not put this heat sink, we put fan to cool it also. Okay, so in your laptops, in your machines, these are exactly perpendicular. Okay, so you have a heat source, then above that heat source we put the heat sink, and above the heat sink we again put a fan for cooling. Okay, so that the temperature of the processor will be controlled, and then you are able to use it for the longer time. Okay, and this happens in many cases. Okay, so this is related to our field, so that's why I have taken this example. But it happens in all the engines. Okay, all the heat engines. So that's what I said, thermodynamics. Okay, all of heat engines, even though your bikes, your cars, your any engine. Okay, where the combustion happens and the heat is generated. So we have to take care, and this is the mathematics for designing that all heat strings. And that's why these topics is having a very much importance in the all field of engineering. Okay, not just in computer and IT. So this is what example we can have, and many other examples we can have. Okay, so I hope I answered your query, Gaurav. Yeah. Okay. So there are many examples. We can think of many examples actually I can give. Okay. So that's why we are learning this topic to design it. Yes. So we are actually designing the heat sinks. Okay. Correct. So let us go for the another example. Okay. So shall we go for the another example? Yeah. Very good. Great. Okay. So we'll go for the another example. Okay. So we go for the example. Okay. Find the orthogonal trajectories for the family of curves P is equal to 2x c. And then only we are able to solve this. Now it becomes homogeneous, and then we are able to solve it now. Okay. So that's why we have to be careful. Now let us solve this. So what we get here. So we have the example. Find orthogonal trajectories for the family of curves. P is equal to 2xy minus x cube plus 3xy square is equal to c. Now let us consider the solution. So let f of z is equal to u plus iv be an analytic function with the imaginary part that b is equal to 2x minus x cube plus 3xy square is equal to c. So here we consider the derivative with respect to y. So we got here, this is going to be 3. Uh, here we have, this is 6 x y. So let it equation 1. And with respect to x, we have to consider. So we'll have here 2 minus 3x square plus 3y square. Let it equation 2. Okay. And now what we'll be having? So we put x is equal to z and y is equal to 0 in equation 1 and 2. So we have. So what we'll be having here? Psi 1 of z0 is equal to 0, and we get psi 2 of z0 is equal to 2 minus 3z square. Okay, so here we get this psi 1 and psi 2. And once we know psi 1 and psi 2, so we are able to write by Milne-Thompson Thompson method. Okay, the analytic function f of z is given as. So what is the f of z you will be having? So integration psi 1 of z0 dz plus I integration psi 2 of z0 dz plus c1. So where we have c1 is constant. Okay. And now we know what is going to be psi 1 and psi 2. So we are able to write the function, analytic function f of z as this is going to be 0 dz plus I integration 2 minus 3z square dz plus c. So it is going to be I integration 2 minus dz square dz plus c1. So this is I into 2z minus 3z cube by 3 and plus c1. Okay. Now simplify this. So we get f of z is equal to 2iz minus iz cube plus c1. So this is the analytic function. So this is going to be analytic function, and hence what we have to do is we have to separate the real and imaginary part. So what we do is put z is equal to x plus iy in above equation. We have, so what we'll get here, f of z is equal to 2I x plus iy minus I x plus iy bracket cube plus c1. Now let us simplify this. So 2ix, this will be minus 2y because you'll be having y square. This I square is going to be minus 1. So we'll be having 2 minus 2y minus I. Here we have, this is x cube plus 3I x square y minus 3x y square, and you'll be having here minus I y cube and plus c1. So it is 2ix minus 2y minus ix cube. This will be I square will be minus and already minus, so we'll be having minus 3. We have x square y. This minus will become plus, so 3I x y square. And now this minus and this minus will be minus, and you'll be having here this I square again minus, so you'll be having this minus plus I square is minus, so minus y cube, and plus you'll be having c1. Okay, so we collect the term without I and with I. So we will be having 3x square y minus we can have y cube minus 2y. So this term is without I, this term is without I, this term is without I, plus I. So 2x minus x cube and this term plus 3xy square plus c1. So this is going to be f of z. And hence what we can do is comparing real and imaginary parts we get. So what we are able to get here, let us see. So u is equal to 3x square y minus y cube minus 2y, and p is equal to 2x minus x cube plus 3x y square. So now verify whether we got the given term or not. So p is equal to 2x minus 3x square plus 3xy square. So check this. So it is 2x minus x cube plus 3xy square. So that is correct. That means our calculation is correct, and hence we are able to get this as the orthogonal trajectory. So what we have here, Hence, we write the orthogonal trajectories of the given family of curves is, so we have dx square y minus y cube minus 2y is equal to c. Okay, so we can write where c2 is constant. Okay, so here we have to be careful. Don't mix up with the constant of integration and the given constant. So we have to use the another constant. So specify that it is going to be the constant. So it will take care of the every constants that we have used earlier. Okay, and this is how we are able to find the orthogonal trajectories for the given v. Okay, so do we have any doubt now in this example? So any doubt in this example now? Okay, thank you.